LAURELIN, a research project funded by the European Union and supported by the Japan Science and Technology Agency, JST, aims at developing innovative solutions to improve green methanol production from CO2 hydrogenation in terms of energy efficiency and production cost. The project's main objective is to introduce a new generation of catalyst systems, perfectly adapted to advanced reaction processes including microwave, magnetic induction, and non-thermal plasma. In light of their ongoing research, the LAURELIN Consortium organised on 22nd November 2023 the first EU-Japan e-fuels research project cluster event. Researchers of 3 EU-Japan-funded research projects, LAURELIN, Oracle, and 4 Aircraft, met at the Hongo campus of the University of Tokyo to exchange their knowledge and intermediate research findings in the field of new e-fuel production methods for sustainable transport. 2 scientific roundtable discussions were held on catalysts, e-fuels, and new generation of chemical reactors. The video of this conference aims at providing relevant training material for students, researchers, and anyone interested in the field of e-fuels and new generations of catalysts for chemical reactors. A roundtable was held on catalysts for a new generation of chemical reactors. The roundtable discussion was moderated by Dr. Raf Roland, Process Design Center, member of the LAURELIN Consortium, in presence of Professor Stefan Wutka, member of the 4 Aircraft Consortium and the Basque Center for Materials, Applications and Nanostructures and EcoBasque. Dr. Jonas Gorauskis, member of the 4 Aircraft Consortium and Instituto di Nanociencia y Materiales de Aragon in Masisik and Arai. Dr. Yun Maruyama, member of the Oracle Consortium and the Osaka Research Institute of Industrial Science and Technology, ORIST. Professor Luis Miguel Martinez, Prieto, member of the LAURELIN Consortium and ITQ CSIC. Professor Andrew Beale, member of the LAURELIN Consortium and the University College London. Dr. Rudolf Emmerich, member of the LAURELIN Consortium and Fraunhofer Institute for Chemical Technology.
To try to amuse you with another roundtable discussion. And this time the topic is closer to the daily activities of our panelists. So we hope that it will be an easier one. Let's see. I will give a very short presentation to introduce the panel discussion. And I hope to give maybe already some ideas, some sparks for the discussion. All right, so we're going to talk about chemical reactors and the catalysts which have to go inside them. First, let's talk about the chemical reactors. What is the job of a chemical reactor? Well, the job of a reactor is to make a chemical reaction happen, right? It is basically to provide the right atmosphere for fruitful encounters. And this is why I would like to make an analogy, as you can see, with 18th century ballroom in Europe. I'm not sure if the equivalent exists in Japan, but it is a good analogy, I think. So the job of a chemical reactor is first of all to bring together the reactors. We need some space for that, and that's going to be the reactor. We have to bring them together in the right concentrations, otherwise it doesn't happen. So you would prefer to have more or less an equal number of women and men doing this happen in your party, and similar for the reactions. You have to bring these into a good mixture, and in case they are not mixing, you have to do some tricks to make the phase transition of the transfer of the reactants from one phase to another. So you can imagine that if you have in your bowl some non-mixing guests, let's say some British and some French, right, in the 18th century, and you want to make them interact then you need some, for example, interpreters or so to ease this. We have to accommodate intermediates such as surface species, ions, electrons, and radicals. Thinking again about the analogy with the ballroom, we might find that some of the guests need a little drink before they become enthusiastic dancers, right? So this is what our reactor also has to provide accommodation for these intermediates and provide them. It also has to remove inhibiting products. You can imagine that if one of your guests has had one glass too much, then it can become a problem for the party. So he has to be removed from the companionship. Similarly, there could be inhibiting products which have to be removed from the reactor. Think of equilibrium limited reactions. If you have a product, it has to be removed as quickly as possible in order to shift the equilibrium the right way. Your ballroom shouldn't be too cold at the start of the party, because otherwise the guests will not be very much at ease, right? So you have to probably heat up your reaction mixture to the right temperature. And then once they are dancing enthusiastically, maybe perhaps it will become too warm and you have to open a window or so. So you have to cool in many cases. In some cases, you actually have to provide heat to sustain the reaction. So this is what a reactor has to do in layman's terms. Then we'll talk about intensified reactor designs. So we have to intensify, or we don't have to, but we can intensify the reactor design to allow a better control of all the variables which are affecting our reaction behavior. And if you make your design more complex, then usually you have more levers, basically, to tune your reaction conditions in the right way to increase productivity and selectivity. With some designs, you might actually enable reactions which are otherwise not possible. And a very useful example there, I think, is the electrochemical water splitter, which is actually has a prominent place in all our projects, I think. So without electrochemistry, that would be a very difficult reaction to accomplish. In many cases, you can also reduce the amount of components present. So the amount, which also reduces the safety risks. I have listed here some reactors to illustrate different extents of intensification or complexification, is perhaps a better term. The fixed bed reactor on the left is used to perform autothermal reforming of methane, for example. But it's a big, bulky fixed bed. There's not too much science behind that. Maybe those engineers who are designing those would be offended if I say that, but yeah, that is more or less the case. In the middle there, you have a ceramic microchannel reactor, which is a device which has been designed to allow very careful temperature control and also to have very good mixing of your reactants. And that can make for a very fast and very selective reaction. Those are typically used, of course, for very exothermic reactions, which would otherwise be very difficult to control. And then to the right, you have the most extreme example there, a dolomite 1 milliliter microreactor chip for mixing and reacting 2 or 3 liquid reagent streams. That would be the most extreme case, I think, of intensification. Okay, here's a list of intensified reactors. I'll talk briefly through this. First, you have reactors with small moving parts, such as the spinning disk reactor. I'm not sure if you've heard of that. Also making for good heat exchange and mixing. Rotor stator reactors, and so on. Then you have the microreactors, of which you have seen an example on the previous slide. You have reactive separations, reactive distillation, for example, which distill off one of the products, or even two perhaps, to sustain the equilibrium limited reaction. Reactive extraction, reactive adsorption, that works similarly. You have membrane reactors, where one of the products, for example, would be extracted from the reaction mixture. Alternatively, it could be a reactant which is actually provided through a membrane. For example, oxygen, which is going through an oxygen selective membrane, which allows the use of air instead of pure oxygen. It could be a contacting membrane as well. There are different supercritically operated reactors exist as well. So these would be used for cases where, for example, you need material transfer from a gas phase to a liquid phase, where the gas is not so soluble in the liquid, so that's problematic, of course. If you do things supercritically, then you have one reactor, everything will be perfectly mixed, and you can intensify things. The final class is field-enhanced reactors. So that could be a sonochemical reactor. Laser-induced reactors exist as well. It's incredible. Exists. Induction-heated reactors, microwave-enhanced reactors, plasma reactors. Those would be the classes of common, perhaps uncommon, field-enhanced reactors. I've marked here with an asterisk electrochemical reactors. Those are not considered traditionally intensified reactors, but they do have in common with the other reactors that they are complex, and that they are, not so much 3D but more 2D. So in that sense, I think they do belong in this list. And also for another reason, because these last four reactors which I have mentioned are actually included in our projects, in our three projects. We have the magnetic induction heated reactor, we have the microwave enhanced reactor, and we have the plasma reactor. And then finally, obviously, we have the electrochemical reactors as well. So we are fortunate enough today to have experts present in this hall on all four of these classes of reactors. What they have in common, interestingly, is that they all have a complex design. If they were not complex, then we wouldn't have a lot of work to do. It's a great thing. They are electrified as well, which means that they are future-proof also. And they have tailored advanced catalysts. And it's about the linkage basically of catalyst design and reactor design that we are going to talk today during this roundtable conversation. All right, so I have three pictures here. The panel members have not yet seen these. They have not seen this presentation, so apologies for having to break your neck to see them. But you will all be given a chance to initiate the conversation later to tell us some more about these. You have here on the left one material which Dr. Hugh has already presented earlier on. So that's MOFs encapsulating a biocatalyst to protect it from harsh environments. We have this porous carbon shell surrounding magnetic nanoparticles, and those shells will be preventing sintering. And then finally, we have for the Oracle project doped carbon surface with elongated step. I'm not going to go into the functions of these. Our experts, of course, can do this much better. But these are three examples of representing all three projects. I could have given many more, but of course, we don't have the time to go into all of these. Here's a nice picture, I hope, of all our panel members, and I'm going to introduce them to you now. And as eminent as they are, I still need a piece of paper actually to tell you their CVs. I'm going to talk first about Professor Stefan Woedke here, closest to me. He obtained a PhD in chemistry at the Humboldt University in Berlin in 2009. After having had several positions in Europe and USA, he is currently an Iker Basque research professor at the Basque Center for Materials, Applications and Nanostructures. Shortly, that is BC Materials in Leioa, near Bilbao. All these gentlemen, I should say, are working in very nice cities. I don't know if that's a coincidence. The research line of Professor Woedke is in the design of hybrid materials from molecular building blocks with precise control of their size, shape, and hierarchical structure. Welcome, Professor Woedke. Dr. Jonas Bulauskis is sitting 2 seats further. He is with the Institute of Nanoscience and Materials of Aragon in Zaragoza. His background in engineering and chemistry gets reflected in his general scientific interests, which is to combine distinct material properties through advanced processing routes in order to gain a novel composite material with enhanced functionalities and highly optimized performance. His current specific research interests are the integration of novel material concepts such as metal organic framework, MOFs, derived catalysts, or enzyme-based biocatalysts within heterogeneous catalytic systems for more efficient and sustainable reaction technologies. Dr. Jun Maruyama is also here, joining the podium now. He is head of the Advanced Carbon Materials Laboratory in Osaka Research Institute of Industrial Science and Technology, or ORIST. He is performing research on carbon materials, especially for electrodes of energy conversion systems such as fuel cells, air batteries, electrolyzers, redox flow batteries, and his strong points are the knowledge he has accumulated about precise pore development, surface treatment, and modification. Those are his strong points. Welcome also, Dr. Maruyama. You are representing today the Oracle project. Professor Luis Miguel Martinez Prieto is also here in green. He is an organometallic chemist who specializes in metal nanoparticle catalysis. In 2017, he was awarded with a Juan de la Cierva fellowship that allowed him to work on confined or supported metal catalysts and magnetically induced catalysis in the team of the famous Professor Korma. I don't know if he's also famous in Japan. In Europe, he is at the ITQ in Valencia, Spain. Last year, he was selected as a Ramon y Cajal researcher and started a new stage in his career as independent scientist in his alma mater, the University of Seville. The Ramon y Cajal project, I have been told, is a mechanism of the Spanish state to prevent the brain drain which they have been seeing in the last decades. So I'm very happy that they allowed him at least to be here in Japan today. So as I said, he is now an independent scientist. He is tenured at the CSIC at IRQ in Seville, and he is the team leader of the Katana group focused on metal nanoparticle catalysis. Professor Andrew Beale, to the left of him for you, is currently a professor of inorganic chemistry at the University College London, UCL, and group leader at the Research Complex and chief scientific officer of Finland Limited company incorporated in 2012, which is also involved a bit in our LAURELIN projects. His current research interests concern the study of functional materials used as catalysts and in energy storage with novel chemical imaging techniques using X-ray scattering and or spectroscopic methods, often studied under dynamic or operando conditions. So Professor Beal here is the only representative in our panel of the characterization studies, which are nonetheless very important for the design of them. So it is very good that you can join us for the conversation. Then last but not least, we have Dr. Rudolf Emmerich, who is a physicist graduated from the University of Karlsruhe since 1994. That's already a while back. He is a permanent staff member of the department and head of the R&D microwave and plasma group. The group is responsible for most of the department's national and European projects related to microwave heating and plasma. He has extensive experience in R&D and application of microwave-based heating systems. And that is also his role precisely in the LAURELIN project. So that finalizes the introduction of our final panel members. I'm going back now one slide, and I will ask some of the panel members to comment on these nice photos or animations also there, to tell us a little more about the rationale behind them, why are they designed, and also I would like them to ask, in order to get the flavor of their daily work, to indicate what would be their main challenge, technical challenge that is in the work. So perhaps Dr. Gurowskis and Professor Woodke, you could comment on the MOFs first.
Yes, so as you all know that enzymes are perfect catalysts that are optimized by nature over millions of years, but they have a certain spectrum where they are working, and we would like to increase the spectrum in terms of stability, chemical and temperature stability. And when you speak, for example, in temperature stability, if you heat up an enzyme, it's not that they denaturate, no, it's they have specific foldings in which they are active. So what we try to do is we use a hybrid material, middle organic frameworks based on inorganic, organic building blocks. Thank you so much. Can you hear me better? So we try to basically force them into a certain conformation by crystallizing the middle organic framework hybrid material, porous material around them, and this increasing the stability. When we're doing like this, we have then our temperature stabilities, and then also the reaction speeds up. As we know, if you put energy in the system, the reaction goes faster, and then also you have more chemical stability because the MOF is a porous framework and can also sieve certain things. And also you have a powder, you have a heterogen catalyst, so you can easily, when you think about processing, you can easily apply them for real-world application. So this is basically the idea in my dream. Basically, for future is that the MOF is then also more active. Also with MOF, you can do a lot of things. You can imagine tunneling reactions. One catalytic reaction makes the enzyme, another the MOF, or the selectivity. So there are different ideas. So, and what me fascinated about these hybrid materials is really that we take things that of nature can control very good, and what we as a human can control synthetically very good, and combine them to make the best of both worlds. And the main challenge in my field, I would say, just motivation and passion to do this, because from a fundamental perspective, it's very interesting, and it's, especially for students, project is very good. You can basically not lose. It's more the question how much you win. And persistence. I really believe that when you're very persistent, that you can do a lot.
Thank you very much. I've been given to understand also that Dr. Gurowski's is responsible for realizing Dr. Wutke's dreams.
Yes, it's kind of a part through, yes, because when Stefan says Eureka, I put my material, let's say, that's my trouble starts. Because I actually need to make that material work in real life application. That's its positioning within the reactor. Because usually you just cannot pour mass within the reactor. You need to kind of strategically position it, let's say, make it enough flow rates and everything, optimize it, and to position it in 3D scale, let's say. As you showed previously some slides, we have, let's say, different supports, etc., with food channels. So that's my job, let's say. I have to actually synthesize it, flip things upwards to make it an anchor position, to organize all that chemistry, to run. And because he's got a challenge, let's say, actually, to make that. And then I have a challenge to position it, to integrate system. So I'm kind of a gap between him and it's a real life application, and we need to try to talk them. Okay. So as we said, and that's our kind of job, as you say, what we do on a daily basis. We're trying to do it. Let's say 80% of our job is bureaucracy, 20% is actually what we do in the lab, and I really enjoy it. It's really, you see on a daily basis, you see new challenges, new reactions coming out, and new problems actually, which we can extract. Okay. I expect that I responded to the question.
Absolutely, yes. Thank you very much, Dr. Gurowski. Professor Martinez then would be the right person to comment on the second image there.
Yes. Basically, we work with magnetically induced catalysis, which is based in the capacity of ferromagnetic material to release heat in the presence of an alternating magnetic field. So, in particular, in this case, we have a core shell cobalt nickel nanoparticles encapsulated in carbon. This is encapsulation in carbon is to avoid the sintering in the high temperatures reached in the catalysis. The advantage of to use this encapsulated nanoparticles is to avoid the sintering. Yes, and the advantage of magnetic induction catalysis is that we generate the heat from inside the reactor, so it's not necessary to heat the walls of the reactor. So the more efficient way to carry it out to reach the reaction conditions. Also, the magnetic induction is the work time is very fast and reach the reaction temperature very, very fast in a few seconds. So it's very convenient for intermittent energy storage because we can switch on, switch off the reactor very quickly. So when a windy day or sunny day, we can store these intermittent energies. So it's the main advantage to work with this new technology, which is very interesting.
And what would you say is your the toughest battle to fight in your work in your daily life? You know, assuming.
I think that the main limitation is we need to work with transparent materials, according to the reactors, to glass or quartz. So it's not possible to pressurize with high pressure the reactors. So maybe it could be the main limitation of this technology. It's difficult to work at high pressure.
So in media for methanol synthesis, obviously it helps to have a high pressure. And we are a bit limited nonetheless. We have managed to pressure with 10 bar, right?
10 bar, we are developing a new reactor that's maximum 10 bar.
Yeah.
That is not enough for the moment, but we are working on that. There are some ideas.
Thank you very much, Professor.
Thank you.
The third image then is the doped carbon surface. Dr. Mariano can talk to us about this.
In the Oracle project, I'm in charge of developing active anode catalyst for oxygen evaluation reaction. The cathode side is actually nitrogen reduction for producing ammonia over regenerated fuel. In my side, this is auxiliary reactions, not for producing directly regenerated fuels. But my attempt to produce such elongated stages is to make catalysts more active because elongated stages are very active for oxygen evolution reactions. To produce these elongated stages, first we have to find the H surface of carbon, and then we coat it carbonation field doped with argon and nitrogen. This work in my daily work is actually try and error. I have to get through many errors to get good results. And to get through these difficulties, I have to search many references. This is one of my approach to overcome the difficulty. And a discussion with colleagues is another way to overcome difficulties. And also obtaining various opinions from overseas, internationally, is maybe a very big approaches to get the idea to overcome difficulties in daily life. Thank you for the opportunity.
Dr. Emmerich, I would also like to invite you to tell the audience a little bit about your work. Unfortunately, you have no image there, but you can comment orally, perhaps.
Yeah, our work is in principle that we want to intensify chemical reactions by microwave, and by microwave is really a little bit similar to the induction. We directly heat the material and not the walls. That means that we have a very efficient energy transfer to the material. We have also the restriction that we cannot use in principle metals. We can have metals with their bigger parts so that we can radiate microwave inside, but it's a comparable sometimes. I'm not restricted to ferromagnetic interaction with the catalyst, so we have a more open in that case. And what we see is if we heat the catalyst with microwave and intensify the process, we have a higher yield of the reaction and a better selectivity, and we have a less energy. That is what in our work we want to bring this microwave to intensification.
And Professor Biel, maybe finally you could also comment on your characterization work, which is obviously of a very different nature, but nonetheless you must be facing challenges as well. So maybe you can comment a little bit on that as well. Sure, yes.
Yeah, actually we're more interested in generating images like that. So we don't actually make the samples, that's kind of a good thing. So we don't really do the wet chemistry. But we're interested in taking photographs or basically trying to get some sort of better understanding of the materials and the property. So we do, as you said, at the beginning, these things do the spectroscopy and the sort of diffraction measurements, particularly under operando conditions. And why do we do this? Well, obviously we want to establish structure activity relationships. So some of the very nice materials you're seeing up here, ultimately the ambition is to try and get some design criteria so that we identify a salient characteristic which can then be overexpressed, particularly in a second formulation of that material to better performance, let's say. Why do we do things on operando, or what does operando mean? I think this is a term that's becoming increasingly familiar, but just for those who perhaps are not so familiar, operando kind of means studying something as it's performing its function. So we typically do a measurement of the performance as well as doing a measurement of the characteristics, so we're checking the spectrum as the catalyst is happening, for example. Obviously those experiments are very challenging because we're trying to recreate the same sort of environment in the laboratory on our instrument, on our setup. So of course there's kind of a bit of a technical challenge to overcome there, not least because we use natural facilities, so we have a very limited window, a limited amount of time to do these measurements. We might be trying to kind of recreate the same environments that is typically carried out in the laboratory. We might be trying to carry out methanol synthesis, which requires a temperature and pressure, and we then need to try and measure the sample as it's carrying out its reaction at those temperatures and pressures, and basically we have to recreate that environment some several hundreds or thousands of kilometers away from where we typically operate. So we have to be a bit, I don't know if this is a familiar term, basically like MacGyver. We basically have to create something typically from scratch and then try and measure to get that useful information. So that's a big challenge. And why do we do it? There's a very nice expression that one of my colleagues in France used once. And he said, the reason we do these measurements is that we see things that we didn't even know were important before we did the measurements. And this is so true, and I hope that yesterday in our LAURELIN meeting, when I was showing some of the characterization data from some of our colleagues' very nice samples, that we start to use that information to understand how best to formulate the catalyst. And at first, I think, okay, some of these systems have been studied before, it's difficult to get new insight, but with some of the measurements we're now doing, particularly under random conditions, we think we're getting that insight. And hopefully this information can then be utilised to develop better materials as part of the process.
Okay. That's an important point, of course. So our projects luckily last longer than 1 month, let's say. They last several years. So we would be hoping that we can use that time to improve our technologies. And I wanted to ask you, how does that work in your project? Is it at all efficient? Do you think perhaps there is an improvement potential in, let's say, the feedback loop between the development of the materials, the tests of those in the lab, and then characterization as well? Just how the experience of your projects. Can anyone comment a little on this? Is it on?
So for me, first of all, the most important is the time. 3 years I find too short for all things, and this is here the basic requirement should be 4 to 5 years. This would be an easy improvement. So 10 years or 4 years I find very optimal because this is a challenge, really a challenge this time. Then things are the for example, in aircraft we have 3 years, we approach now for 4 years, so the funding is not excellent, but every 4 years because you just need the time, especially for these EU projects. I really think that you need 4 to 5 years for the funding that you also And then another challenge is with this project I find is interdisciplinary research. You know, you also see from Jonas and my discussion around that we live in really in different worlds, and you need really to speak very often to understand each other and then to push things and science. And there, I don't know, in the project this should be also more aware of and further funny. So that is really that we can meet also in person more often. Video calls are nice, but I would really, this is also here in Japan with our collaborators, we meet in person and discuss the things. I don't know, it speeds up so much. So these 2 points that time, also 4 or 5 years, I would really like to make that project and that focus on meetings that we understand each other.
Thank you very much. Any other comments, perhaps, from the other panelists?
My case is similar. No, it's highly important to have a continuous feedback between characterization, analysis, and also characterization process. It's very important to know and to improve your catalysis, what is happening during catalysis. And sometimes the only way is to better characterization. We observe the paradigm system. I think it's highly important to have a continuous feedback.
Yes, so we have now touched upon the subject of collaboration, multidisciplinarity, physical meetings also. A physical meeting like this in Japan is excellent. We like to be here. We enjoy the hospitality and food of our Japanese hosts, but they are also very expensive. And it's flying here and back costs us more than 1,000 euros. I don't know, in yen, that sounds even more impressive. So, could you perhaps elaborate a little bit on the advantages of collaborating with people from other nations, and maybe specifically, if you can, of the counterparts of Japan or the Japanese? What are, let's suppose you have the same project at the national level, would that work the same? Would that be equally successful, you think, or would there be something missing? Yes?
I'm sorry to then I give up, but I really like this question. I would like to highlight, you know, my research is material research, and I like to add different functions to make synergetic effects. And this philosophy I like also at the human point. And the thing is, you know, we spoke about the kitchen. You know, we have kitchen everywhere in the world, but everyone cooks differently. This is the same in chemistry. Everyone approaches science differently. And for example, in my group, I don't have any nation double. So each of my group members, nearly 9 here now from different nations. This is important because different nations go approach science differently. And with this, you come on things that you would never come up with. And especially about Japan collective things like this, you know, have a very distinct approach to things. And this is really helping you to find ways, new ways for yourself and for your science that you would not find, you know. So this is so different nation diversity, synergistic effect. This is, I think, key in science and also in the research direction, because the scientific question that you're writing, the problems are too complex for one group, in one nation to solve them alone. So it's really absolutely needed that we team up.
My comment was very similar. So in our project, I don't know how many nationalities we have. So 5, 6, 7, but I'm not sure. Again, I counted and say, and we just counted the countries. So really, really interdisciplinary project and plus internationality on top. So we really need to organize our ideas and everything to actually to be sure
but we are expressing ourselves or communicating everything in a clear manner, and it really helps. Especially for me to organize myself too.
Then your view, it's a difficult question, I really imagine. Then your view, perhaps say something about the way for the Europeans, Japan, or for Japanese, the EU, how the counterpart is working, how that surprised you, or if perhaps you have learned something about this.
I mean, we constantly learn things, and was it was like, I mean, it's the first collaboration in Japan was, and we really enjoyed it. Sense, but we have very systematic colleagues working in a specific field for electrocatalysts, and the knowledge which we were acquiring too for professors because it's very, very, very valuable. And he reactively participate in different packages, especially leading work packages, say for catalysts. So we are kind of learning a lot, and plus we are kind of providing our feedback too, let's say, in case when it comes to filtering down, we are kind of trying to push ourselves to the same catch up on some specific electrophysics things.
I would like to ask you about the scalability of your technology. Is that an issue? Have you been thinking about it? How are you trying to? How will you be trying to solve these issues? That would be interesting, I think, for the audience to hear.
Microwave has a little problem in scalability. It's the barriers to wavelength. Normally something about 30 meters or 37 meters. It means the simple scale upscale is not possible, but it's a modular upscale you can do. So in principle, it's a little bit complicated than conventional technology to upscale, but scale this without any bigger problems.
We have a similar situation with magnetic induction catalysis because it's not easy to scale up the coil and the reactor. Oscillation is not the same in conventional heating that you can easily scale up. Like with a bigger coil, which is down. It could be a problem, so it's more for medium scale. For
So if you think about the first generation computers, I think they were still manually soldered. Currently, computers are, of course, produced by machines. So could that be part of the answer, perhaps robotization of the production of the reactor?
When it comes to photograph, a big part of it is for the work package, which I'm responsible for. It's actually its stability. Because we deploy different techniques which are based on additive manufacturing, which means that scale is not an issue. Hardware can be, let's say, segmented and produced in a very fast way because, as you know, processing, if we're going for conventional processing routes, etc., fabrication of specific support scaffolds, it may take months or even, in some cases, years to actually produce the processing line. When it comes for additive manufacturing rooms, it's really good tool actually to go from very, very small scales, let's say millimeter reactors, to actually 100 or 200 or 2 or 3 liters, say, volumetric scales. It's really very easy because it's just
simply scaling it in the program, it just produces it. And we're talking about a time frame of 2-3 weeks maximum. So it's very fast. We based these choreograph project just to be able kind of to expand and go very fast from one terrain level to another, just due to this ability. So that was a catchy point, I think, for our project, and actually get the funding from uni to. By the way, if there are questions from the audience, we can also have these without any problem. Oh, there's one.
Can you comment on the advantages and disadvantages of scale up versus scale out of the various reactor systems?
For me, advantages of scale up.
Scale up versus scale out. So, in other words, making reactors bigger versus making reactors in using parallel.
Yes, maybe it could be a solution with reactions in parallel, or maybe used not in a big company or in a big industry, instead in many scale or something to take. In the case of magnetic induction, to store the excess electricity when you produce. So it's not necessary to have a big reactor to do that. In my case,
I think it's similar to the microwave. We have them more flexible, more production line. This is the thinking behind this. So then perhaps we have which is available for the short time. We have no time for heating up the reactor, so we can flexibly start and stop with such modular reactor.
I mean, from the accessible point of view, I said that we need to deliver specific structures, especially it should be like a gas system. It's much more easier kind of to avoid errors if you're talking about segmented reactors than just huge big one. And one small people can do even everything for huge reactors. So segmented small scale, it's much more better in the sense for processing that as me to avoid kind of errors, because not errors but failures actually in huge reactors. So that's for specific areas, let's say. Dr. Mariana, perhaps. Okay. Any other questions from the audience? Yes. As well. Yes.
Thank you. On this slide, I know that the group has developed very complicated transfers. I think complexity, introduction to complexity is an important way to develop new catalysts. It seems to be very hard to get an idea what kind of complexity is important for certain reactions. But at the same time, resiliency, introduction to resiliency in complex systems also very difficult. So once you even have ideas how to create such kind of materials as a catalyst, what kind of effort do you have? In some cases, we said internationality or nationality may give us some new state of evidence because they will do some sort of different approaches, even though the same material. So this could give us some new materials. But it's It's very hard, something they know what, so.
Thank you for this excellent question. I would like to cite Leonardo da Vinci that said simplicity is the ultimate sophistication. So at the end, when we thinking about fundamental science to application, yes, it's the researcher for fundamental researcher for physics. What you said, that we thinking too complex and making complex ideas that will never reach real world application. And maybe this picture looks very complex, but at the end, I can tell you, so also our science is that we try to find straightforward, simplistic answer for complex questions. For example, this is why, as I told you, enzymes are quite complex, and I have also research directions, where we're trying, enzyme catalysis. One theory is the electric fields that are created during the catalytic reaction in enzymes to reproduce them in mouse. Richard Feynman, but we cannot buy, we do not understand. So I try to buy enzymes, but this is very complex. This is for fundamental purpose. But for application, I just say, okay, enzyme is optimized, and now I increase the application range of this perfect things in a, I would say, straightforward and easily upscale way. And simplicity means that it's reproducible, that it's cost efficient, and hence interesting for industry. So I think this is a very important point, that all these systems are sometimes very complex. We need to make it as easy as possible for fundamental science, because if not, you cannot translate it. So thank you for an excellent question.
Yeah, just to echo.
Just to echo again, really great question, because I think I look at this from a very different perspective. What is actually in that catalyst? Where are the elements? As you said, you're trying to make something in a way that you can control to get a homogeneous distribution, but actually maybe the critical element in that catalysis is this kind of inhomogeneity, or this kind of difference in the properties across a particular volume of the catalyst. And that, I think, is really still a very big challenge. Yesterday, in our meeting, Adolfo put up a table and it had the performance of 200 catalysts that had been assessed for CO2 conversion to methanol. And we were trying to benchmark the performance of those catalysts in our project. But even looking at that table with all the performance in there, we had some questions like, how do you get that sort of level of performance with that catalyst? So I think one of the big challenges is the benchmark. So what do we decide we're going to target when it comes to designing a catalyst? And then, of course, the challenge is for people making these catalysts to be able to do this in a reproducible way. And I think one of the other big challenges we have to think about is, ultimately, if we're going to sort of use this technology as a replacement or as an alternative way to produce a product, then how scalable is this production? And then there's an element of design in that we have to factor in. So if we take, for example, copper, zinc, aluminum catalysts that are used industrially for ethanol synthesis, they often have carbon added as a lubricant so that they can produce the catalyst on a ton per minute scale. So I think, you're totally right that we have this big challenge, although of course there's a lot of literature that we can refer to, and we can therefore import some of those findings when we're sort of designing materials now. So I think, when we're trying to kind of design materials, we all have to bear in mind this challenge of scalability, particularly as was highlighted this morning. We don't really have as much time as we would like to try and take a new process from conception all the way up to scale. And I suppose going back to the previous question, I think parallelization or scaling out might actually be easier in that sense. If we're trying to produce catalysis on a scale basis, because I assume we need a small amount of catalyst per unit. That's a bit easier than trying to produce things on a massive scale. And maybe where microreactors will actually be a bit more advantageous than working at such such scale.
Do you think we have an advanced analysis system in all?
Well, I have a vested interest, so I would say absolutely. You know, you can't do enough advanced characterization. Please form a queue, and you know, we can have. It's interesting because a lot of people who work in catalyst preparation always say, "Oh, we need to do much more characterization." And as a person who does the characterization, I have to say, there's only so much to learn from this. You guys need to design better catalysts because we can't, you know, we can only really see so much. And I think, you know, that we can get quite a lot of information from an operando experiment, but the thing is we're normally using one, maybe two characterization techniques. So then the problem is, you know, you're only going to see a small portion of that particular element of the catalytic process. So we might be able to sort of tell you something about the catalyst, you know, the local structure and the extended structure, but we're not actually seeing any absorption events or desorption events or action catalysts. So we then try to make some sort of rational judgment on what we think is important, but we've only got maybe 20% of the information. But, you know, maybe that information is at least a starting point for looking at how you can optimize the catalyst further. But I think when it comes to understanding these sort of processes, you know, going back to one of the earlier questions, you know, where the complementarity is probably needed nowadays, it might be that in Europe we don't have that expertise and we need to look more widely. And I think this is one of the things we found in our projects. You know, we are working with colleagues in Europe and in Japan that have got very complementary skills, you know, excellent in areas that kind of enable us to achieve more than the individual sum of the parts project. So, you know, I think this is also going to be good for us when it comes to identifying and seeing how characterization techniques can give information. Then hopefully we're at this stage of the project that information could be utilised to design the next generation of catalysts.
Chris, do you want to ask out time? Just in terms of I'm just going to be talking about placing these two questions together. Parallelization allows you to do things on obviously a small scale, which you can then do on an upper endo basis from a perspective of the reactor. When you think about larger scale reactors, how much influence does that have on the characterization of catalysts? Not just from a perspective of actually doing that characterization, but also the nature of the catalyst you've got there.
Yeah, that's a good question. So, of course, I think as things scale, then of course everything scales, not just the reactor, but the catalyst and the catalyst, the volume that's there that we're working with. And one of the very simple problems we have is that we're trying to get photons in and out of our setup. And the more catalysts we have, the less photons we get out. But there has also been a revolution in terms of our capability to do these things over the last 20 years. So the facility that we use is getting brighter, and actually through brute force we can now see through things. We can actually see through stainless steel. We can even measure sort of components that are several centimeters thick now. So does it mean that we're able to kind of cover more of this, say, reactor design than what we would have been able to 20 years ago. 20 years ago we were limited to small, milligram quantities of material. Now we're looking at grams. So that is kind of a recent development. And I suppose with further developments in brightness facility, in theory we can study even larger quantities of material. But it just comes a limit to how absorbing something is, how much information you get from it, sort of a time scale that is relevant. And I think that's the current challenge we have, is the fact that we can do measurements on large volumes, but you then sacrifice on the time resolution. And of course the time resolution is good for kinetics, and then we need kinetics. So I was talking with Pierre on the side, and of course
a way to understand, for example, mechanism, to understand or to improve on reactor design. So I think there's scope for more work in this area, because it seems that we don't quite have a nice feedback loop there in terms of the information we're getting from some of these studies and reactor design. So catalyst design is a pathway to think a bit more clear. Reactor design is something that people aren't really able to do as well yet.
Can I maybe interject a small question? So you have done this operando characterization successfully already in the LAURELIN project, but we don't have any electrochemistry. Can your techniques also be used in electrochemistry? Has there been any work on that?
A simple answer is yes. There's no limit, really. I suppose the challenge often with electrochemistry is what I've done in liquid phase, and that brings with it its own challenges. And I think, as was highlighted, I think in the Oracle project, sometimes you'll see side reactions, which then when you're trying to do an operando measurement, there is that question of what are you measuring? It's also true with gas phase. But I think, there's a lot of experience studying with gas phase, basically thermal activated processes. So that allows you to, I think, get a better understanding of thinking, structural function. But I think studying of the electrocatalytic events in the liquid phase is a bit of a new frontier. But there are colleagues around the world, as this is definitely a growth area, who are now starting to tackle this problem. So I think this, because of the interest and the importance of it, I think this expertise will gradually develop and improve, such that I think now I think it's also true, and maybe even as we continue to progress, we'll get better at this. So I think, the simple answer is, we can do these experiments, or at least the community can do these experiments, and I'm sure that they are giving insights, and again, allowing us to do the same sort of feedback, or carry out those feedback loops that allow you to then improve on formulation problems.
Thank you. And also, you have waited a long time.
Yes, thank you. Well, my question is the following. Well, we are solving all the problem related to the scale-up. Example, we are all the time these are for call, but I am thinking about operation expenditure, maintenance problems, maintenance challenges of this intensive project. My question is if we are thinking of it. My thing compared to traditional thermal reactors, you expect more expensive expenses on reports, on maintenance, on operation of these kind of reactors. For example, I'm thinking microwave reactor, the quartz reactor, what is the life, what are you expecting life of this kind of integrator? Or thinking about the electrochemical reactors, the time life of the electrolyte example is a challenge. Of course, we are thinking that we have innovative catalysts under different conditions, physical conditions than the usual, different variation than the traditional catalyst. This probably will affect in different manner the stability of this catalyst, the regeneration of these catalysts. Well, my question was if the experts has to think about this. Once we have scaled up, we have a huge reactor or farm reactors.
I can easily see our conservative industry opposing indeed because of perceived lack of robustness. Right? So, Dr. Girarski.
I mean, in our case, let's say the materials which we work in normally is like solid oxide materials. So, in the sense of long-term stability, etc., and quite robust. Coming from a field of solid oxide cells, and for me working down at temperatures and below 300 degrees C is quite stable. And in particular case, in our chemical reactor, our membrane is made from a layer of hydroxide. It's not from a layer. So that's a real challenge to actually do establish processing routes, etc. Because it's new material to work with, at least for me. But it's we went this way, just thinking about, let's say, long-term stability of our system, not going to commercial along the ways.
There are no further questions from the audience. Yes.
Thank you very much for the talk. I think your group succeeded in the good collaboration between EU side and Japanese. But actually, it is very difficult to send our sample to evaluate in EU, actually. So I think, generally speaking, it is very difficult to achieve a good collaboration between ethnically separated place. So I'd like to ask you, what kind of system or what kind of consideration is very important to achieve to improve our preparation between based on your experience?
Just practical one for me. Once I tried to send some form, and I put all the papers in my way, etc., how we expect us. I don't think we arrive. And next time I just put it to the bag and send it by post, and it arrived. So it's still here in the system, but it's a standard mail. That's just practical, you know. And I think it's both ways working, as long as you don't provide too many details. Because, maybe I'm talking too much, but it's just practical suggestions. If you put too much details for custom service, we call it. Which for them it's something strange. We don't understand about these modules. It's something out of their area, and if it's strange for them, we just stop it, and you don't know how many months it will sit in the custom service.
Yeah, we meet such many troubles to send our sample to our place, but so we cannot overcome such a problem. But to develop more constructive relations, do you have any idea to develop our cooperation? So
at the end, I did communication. So yeah, it's two ways. So for a project, it's very good to have good voice. It's in our case Vanessa that really looked at the milestone and things that we reached us for the PIs, and then in our case, what for me personally is important that also the students between different groups interact. So you have these groups where professors are involved, and then you say, okay, if you have a project, for example, with characterization, then the students you connect them and say, you go, because sometimes it's really for them a bit easier than going to the professor way, and I really recommend this that the students understand each other and things really up. It's my experience. So it's,
framework, even communication or opportunity to discuss this discussion.
Yes. Also the two communication said the official one. That where we have work package meetings, where we discuss everything. But the second really important one is where the students just like working colleague friends just communicate over WhatsApp and exchanging, making pictures and sending on just between each other's with data and discussing there. These communication channels, I think it's very important because this is then basically on a weekly basis. For example, with this synergy, you see more an enzyme, so there are two groups enzyme group and the MOF group, and the two students that are working on this, they really communicate weekly about their courses, and I think this pushes things really up.
Maybe I can add some words from my side as the coordinator of the project. For us, I would say it's always important, to improve or try to ensure this communication. So this, I would say, is the key point. And in our project, we were very lucky that Professor Granada traveled quite a lot to Europe. We were not so lucky to come here to Japan so many times, but I would say that in addition to this very structured way to how to manage projects and to have these official meetings, as I said, and also non-official meetings, you should talk too much, but in addition, you should always be in touch in person, because this kind of networking that we are doing today is not the same if you are doing online. And we could figure out these kind of discussions during the working times, let's say, and also in these social events that we are doing. It can even further our research, and this improved our results. So in a way, all the times that this is our money, that is an investment. We are ensuring that our research will meet our goals and will be a better position at the end of the project. So this is very important to increase the presence and these in-person meetings. Of course, not every month, but at least I would say 2 or 3 times per year is needed. And this is very, very, very welcome to have it. And then in addition to the exchange of samples, this is always very difficult. Well, when you have like small samples, this is not a big challenge. But for example, now I'm imagining in all projects that I'm coordinating, we have like huge industrial scale devices, and always through customs is an issue. So this is something that you should get wait, be patient, and will come. And you should keep this in mind also in the project, that you cannot do faster things that we need time, but to do your best, please improve the communication. I think this is the key point. Thank you.
We still have some insight. Thinking perhaps lots of software. In Europe, I believe that past 5 years, we have seen quite a substantial data. And corroborate this. That's asking this is it easier to find funding, to find the right people. Want to go back to it.
I think both is complicated. You obviously you have to find the right people, you have to find the budget. And it's highly competitive, the national funding also, or the European funding, so it's complicated and it's complicated.
Totally agree. Of course, the UK situation doesn't help to find this situation there. Any of the last 5 years was not really helpful. But I think this starting to see the business change a bit in relation to the LAURELIN project. We just recruited 2 new people, including somebody from Spain. So I think this is kind of like a start of the side. Especially the UK has decided to associate with Rise in Europe. So this I think is kind of a good thing, but again, it's the backdrop of I think the challenging problem scenarios. I think the sort of the area that we're working on is very topical. I think there's at least signs that the government is aware that this is very important. So I'm hopeful that there will be continuous funding, I think, for all these areas. I mean, we have a national sort of strategy or initiative in development anyway, so I think this is again an acknowledgement of the importance of this, although this of course tension against all other funding sort of streams that the UK government through the research capital is trying to achieve. And there's also a lot of focus now on translating this to the technology. So I think this is perhaps a slightly more attractive time for early career scientists, particularly they engage with this translation. Because I think it, I think these are sort of skills that are becoming increasingly important. So I suppose we're also be slightly wary about the impact on fundamental research. There's still a lot of value for this, but at least understanding of where some of these ideas that we turn into issues of where they may head. Particularly if people are able to kind of get those skills in undergraduate training schemes and even maybe before that. I think, I'm very optimistic that what we're doing will continue to be relevant and provide good funding opportunities, and that will enable us to carry on to do what we're doing even better.
I agree, and more than agree, more in my case, because I'm a young scientist, so it's from the south of Spain, so the money in Andalusia is for research is very scarce. So it's in my case, it's maybe more difficult to find the funding than the students. I agree with both. Because to accompany students, but motivating students to collaborate in the world is thanks for it.
Go ahead. Yes, I will. So I would say for me, both have the same problem. This is timing, which is pretty hard to align. For example, if you have a very good student, you want to have the money for it, and if you have the grant, you need to have the good student. And both to align, this is the key challenge. And there, I think it's a lot of improvement. For example, I never understood that these individual grants for excellent students, the decision, sorry, this can also go in 2 months, also things like this. So timing is the key problem. If you want to optimize it, then this is, I think, the key challenge I find, because funding is there, so it can always be better on those things like this, but this timing issue I find quite challenging, because when you have good students, then if you don't have actually a grant and then a scholarship, then it's minimum 6 months to apply. Yeah, this is I find this is the key challenge for others.
This is perhaps a disadvantage of the academic system. It can be improved. Dr. Mariyama, can you comment on the Japanese situation?
At least for me, because my institute is actually local one, municipal or prefectural, not a national institute or national university. So there is a very, very limited chance for us to involve in international collaboration project like this. So this is this Oracle or Cyborg project is really a good opportunity for us to the international collaboration. So this opportunity I will give our institute very good knowledge or experience to be involved in international collaboration. Yes, from now on, there will be a limited chance as well in the future. But I hope the collaboration, international project, I want to be involved more in the international collaboration. This is my opinion. Thank you.
I think we have very few minutes left. Maybe a nice question to wrap up this conversation would be, what do you like most about your work? What keeps you going? And what would potentially keep you from going? What would you like to outsource your daily work on? So perhaps all of you could comment on this.
Was there like work in the institute, work in research, also meet people, something like that? What I don't like is that ministry, things, sure. There's a reason why I got in management study this, and but it has to do. Also, the proposal writing is very important.
Amen. I suppose what we like most, I suppose, is that when we do those measurements and we see something we didn't expect, that you're the first set of eyes to see something, that's still very exciting after this time. But I could echo Rudy's comments here, the admin is the real pain, and it seems that it just increases. So sometimes when I see an email from Luis, as much as I receive emails from Luis and I see a spreadsheet attached to it, I think, oh, here we go. Sorry, Luis.
So in my case, I hate administration stuff because I spend 40% of the time doing this kind of things. I love discussing with my students. Maybe when you think you have an idea, and the idea gets real with the society.
I really love about my job. Every day is different. Every project is different. So we're changing. It's not like skills actually. So that's I think it's common. We like to do science and it's different for jobs. But I really hate about my job. I hate myself. That was this administrative part. And it's just saying it's killing. It's killing them, especially so Johnson. It's a huge part of our work, and it's not scientific work. It's nothing to do with that. And I would like to sound as an advertisement. If you want to do science in Spain, good food, good climate, and lots of sun, and late, kind of dry climate, because there is a process dry climate, we'll always have open positions. Anyone know?
What do you mean by outsourcing? That you would prefer if someone else could help you with a particular task or take it over.
Actually, yes, our institute has very good chance to find such people, PhD students or even students from overseas, because as I said, we are a local institute. So another option is I try to involve companies, industries to collaboration. This is our institute strategy to research works. Doing research together with companies. One is outsource.
And what part of your job do you like most? What part of your job do you like most?
Actually, doing experiments myself because I can find the new finding in autonomy and just collaboration with colleagues. And yes, international collaboration is my favorite student.
Yes, I just can, what I like also is it's quite obvious for all of us, all administration works, it's really, yeah, this needs to be taken away from scientists because we are scientists and not manager, and this needs to be highly, I would say, all of us would like outsource. What I like is certainly science, I'm passionate about is to see the successful ideas, you know, when students are successful, this is really making this, and then also the collaborators. I think one advantage why we are not in industry is, you know, in science you can choose with who we work, collaborate with, and you know, this is different culture, different areas. This really gives me huge pleasure, and you learn a lot along the way. So this is, yeah, this keeps going and makes fun to learn always new things.
Yes. So some administrative support would be highly welcome. You can also question the efficiency, perhaps, of these professors being involved in these administrative tasks, because their pay is perhaps too high for this.
Can I ask how this is in Japan, the bureaucratic process? I forgot this just came up, the question. How is it high? Is it okay?
So what is the administrative load perceived by the Japanese researchers?
In my opinion, the Japanese and Spanish systems are quite similar. There's a lot of administrative issues also on the Japanese side. I cannot tell you if it is more or less complex, but there are a lot of extra work for the professor, not only at the scientific part, also administrative tasks. But we normally have a lot of help for the administrative person from the university. They probably normally do that, and also secretary. So that's a very nice help. But it's true that still, so there are some administrative practice similar to school. Thank you very much for the discussion today, Oliver, and some interesting, and somehow you already the answer your and so I'm James Keith. So I'm a combination of the administrative from point of view. But yes, we do understand that this is not the job of scientists, but somehow we need to ask some board or ask write proposals for funding, because we need to really our mandate is to really fund the really great project like yours. So for us, this is the for using the public money for us, it's really important. Your agency, your comment is always welcome, and I think the important side researchers is really helpful for us to design the future funding program. So please do not hate us more, but we are always willing to cooperate, and we are always happy to hear whatever your comments, and we as you and we wish we grow together.
Yes, them as well.
Find out more on laurelin.eu.